last talk, let's also give a round of applause for our terrific organizers. It's been a fantastic conference. Thanks so much for making this happen. Yeah, so congratulations, you survived. You didn't get eaten by a bear out there or succumb to the fatality at cheese night, so good job. Yeah, so let's have some fun. So this talk, I kind of had this vision for this talk, I don't know if it's exactly going to work out this way, of doing things in a little bit of an inverted way, where instead of giving you the story of why I'm trying to prove the theorem, and then giving you the theorem, and then maybe running out of time and not even saying anything about the proof, I want to start with kind of the cool tricks, like how you do the proof, and like talk about those parts, and then kind of build up from that to, oh, what was the theorem? Like, what were we trying to get? So let's try this out. Okay, so let T of Rn, I don't know if you've seen this before, although I'm also going to call it T of Sn minus 1. So I'm also going to call it the Tits complex of spherical geometry. So let this be the realization of the partially ordered set, or poset, of linear subspaces of V, which are contained in Rn. They're not allowed to be all of Rn, and they're also not allowed to be 0. Okay, so that's the Tits building for Rn. And I want to consider this and the affine variant. So I don't think we saw this week. The affine Tits building, which I'm also going to call T of Euclidean geometry. And that is almost the same thing. So it's the realization of the poset of affine linear. So it's like linear, but it doesn't have to go through the origin. Subspace is U. So again, they're not allowed to be Rn, but now they are allowed to be 0. 0 is okay, as is any other single vector. The thing that they're not allowed to be is empty. Okay, so it's a complex that has one higher dimension. And I'm thinking of things geometrically, so I'm going to call these the Tits buildings for spherical geometry and Euclidean geometry, because when you have a linear subspace of Rn, you're also getting a geodesic subspace of this geometry by intersecting it with the sphere. And similarly, right, these are exactly the complete geodesic subspaces of this geometry, at least for the positive dimensional ones. Okay, great. So here's a theorem that, I don't know, you might have seen before. Right, this is kind of the fundamental theorem about these things, and it's the reason why there is a theory of Steinberg modules. So it's the reason why we're all here. Well, okay, at least for Steinberg modules people. Maybe the Polylogarithms people would be here regardless. So, right, so the theorem is that this complex is homotopy equivalent to a wedge of spheres, and the dimension of the spheres is 1 less than the dimension of the geometry. So similarly, there's an affine version. This thing is homotopy equivalent to a wedge of n minus 1 spheres. Okay, cool, right? Although this theorem in and of itself isn't quite as useful as you would hope, because you really want a description of what those spheres are, right? In other words, you want some presentation of the Steinberg module. Okay, so these both have Steinberg modules, of course. So the Steinberg module for En is the reduced n minus first homology of that Tits building. Okay, so that's good, but what you really want is a presentation for the Steinberg modules, right? That's when you really get cooking. So what is the presentation? So I can just start naming spheres here by naming apartments. Okay, so let me do the affine case, since we've seen the linear case a few times. So if I have points x0 through xn, n plus 1 points now instead of n points in En, and suppose that they're affinely independent, so their affine span is the whole space, then I can define this map from the boundary of the n simplex to the affine Tits building. It's really a map from, I take this boundary and I barycentrically subdivide it. And how is this map defined? So Jeremy mentioned we have to draw this picture like 8 times this conference, so let me try to put some points on the board here. So we're going to take our points, we're going to take their affine spans, so those all give us points in that affine Tits building, and then we subdivide the rest of the boundary of the simplex. So here I'm going to cut these line segments up, and then for each of these vertices, I'm going to put the affine span. So it's all the same as before, except now I'm talking affine spans, right? The smallest affine linear subspace containing these points. And then it's pretty clear where to send those one simplices, and then you similarly do the rest of the triangle. Okay, so that gives you a map from this boundary of the simplex into the Tits complex. This is homeomorphic to an n-1 sphere. And so the idea is, right, these are the spheres in this decomposition. Except no, there's too many of them, right? So when we do this, we overcounted the spheres, and so we need relations as well. So these apartments, right, so this map is the apartment of x0 through xn. So these generate, but you also have relations. One relation is that if the affine span is, if they're somehow not affinely independent, so if the affine span is not all of En, then the apartment has to be 0. So you just kill all of those. And then the other relation is that you get an alternating sum if I take apartments of, so I take an n+2 tuple of points, but now just successively remove one point at a time from the tuple. So y0, say yi is removed through yn+1. Then the sum of all those homology classes has to be 0 as well. Okay, so once you do those two things, then you get a presentation for the Steinberg module. This is the Lee-Sharba presentation. All right.
Does it say x? Oh yeah, you need n+1 points to get a
n+1, yeah. Right, we had n+1 points before because of the affine case. So now in this relation we have n+2 points, and then we remove one of them, so now we have n+1 points again. Great. Okay, so we have an apartment for every one of these tuples of points, and if you stare at this picture, what you probably end up doing without really consciously thinking about it is you don't just think of this as an abstract picture, but you think of it as a picture inside Euclidean space, right? This is a polytope. This is a simplex in the geometry, and that simplex in the geometry goes to an apartment. So the really cool fact is that the same applies for any convex polytope. So every convex polytope in the geometry also gives an apartment. Okay, so convex polytope, that's a convex hull of a finite set. And when I take the boundary of this, so that polytope is still homeomorphic to a disk. So when I take its boundary, that is still homeomorphic to an n-1 sphere. Okay, so now how does this map work? So again, I'm going to take a barycentric subdivision of this. The faces of my polytope are not simplices, but once I take a barycentric subdivision, they become cut up into simplices. So now I get this complex that has a k-simplex for each flag of inclusions of faces of the polytope. So those are faces of P. Okay, so now in the Tits building, I'm just going to send that. I'm just going to do the most obvious thing. I'll just send that to the flag of inclusions of the spans. And so that's the simplex in the Tits building. So, sorry, Jeremy, now I'm going to draw one that's not a triangle. Right, say I have a pentagon in the plane. Then I have these points. Say here are two of the points, xi and xi plus 1. Then I'm going to map this whole boundary of the pentagon into the Tits building. That point's going to go to the span of this. That point's going to go to the span of this. I'm going to subdivide it. This point's going to go to the span of the 2 points, and so on. And you can kind of entertain yourself by trying to draw a bigger polytope and seeing where everything goes. Right, so when I barycentrically subdivide this, I get something like this. Oh, I should use a different color. All these lovely colors here. Right, when you barycentrically subdivide this, you get something that looks like this. Hooray, those are all simplices. We get a map to the Tits building. Okay, so here's a much bigger generating set. That makes us be okay.
Why did it need to be convex? Why did it need to be convex?
It certainly works if it's convex. If it's non-convex, then depending on your definition of non-convex, so the definition I would think of for a non-convex polytope allows for the polytope to be disconnected or to be a union of convex things, so it wraps around and creates some different homotopy type. And so then in that case, this won't be a sphere.
Okay, but it would be a map from the space. Okay.
Yeah, that would still make sense. Yeah. That's even more general than that. Yeah, okay. So we have more generators, but now there's a problem, which is now you need more relations, right? What should the relations be if we take this bigger generating set? So if you think about it, probably the first thing you would guess is the following. So I take this polytope P, and I say if P, let's have a line here, weakly subdivides into polytopes P1 through Pm. So let me first just draw a picture of that, and then I'll say what it is. So what does it mean to weakly subdivide? It means this. So there's P1, there's P2, there's P3, there's P4. There we go, P5, P6. Okay, good definition. What does it actually mean? So you have finitely many polytopes whose interiors are disjoint and their union is P. So I've cut it up. And I said weakly here because I'm not assuming that any two polytopes intersect along a face. So for instance, P3 and P5 here, their intersection is this, which is not a face of P3. So you could insist that they restrict along a face, but I'm not going to do that. So this is a very weak notion of cutting one up into pieces. Okay, so if this is true, then the apartment class for P is the sum of the apartment classes for the PIs. That's the relation. So in a sense, it's more complicated than this one, right? Because it doesn't have as much of a rigid combinatorial structure to it. But in another sense, it's simpler, right? It's just that. It's just additive over pieces. Yep.
Elementary question. Why does it map to an apartment there? I mean, I see that every simplex maps to a simplex. Why is it an apartment?
Oh, you know what? I'm not a combinatorialist, and so I actually don't know what the combinatorial definition of apartment is. So I'm not going to claim that this is actually an apartment.
Okay,
I'm just going to claim that it's a map-in from a sphere, so it gives a homology class.
Ah, okay. You're just saying it. Okay, it maps to something.
I would like to learn what an apartment is, so I can check whether this is one or not. But at the moment, I'm not equipped to do that.
Yeah, I wouldn't see why it would be an apartment, but I would also. Could you? Okay, then again, why is it clear that it's a sphere again?
Oh, so a convex polytope. A convex polytope is homeomorphic to a disk. So this is.
No, I get why the left-hand side is a sphere, but why is that a continuous map to the geometric realization? I don't know. So maybe that's.
Well, you just define it on each simplex separately, and then you check that it agrees along the faces of the simplices. So therefore, it's that makes it a continuous map from
just
here to here.
It's a sphere on the left. Yeah. Okay. Sorry. So it's not clear that it's a sphere on the one sphere on the right. This is what I was saying.
Ah, yeah.
Yeah. This is not what you work.
It's just a map from this sphere into that complex. That's good enough for me. All right. Thank you. All right. So a way of stating this more precisely is if we let the polytope group Pt of En be the group of polytopes up to subdivision So let that be the free abelian group on the convex polytopes, modulo this relation that when P decomposes in this way, the class of P is the sum of the classes of the PIs. Then the claim is that this polytope group, so this presents the Steinberg module. So in other words, this polytope group is isomorphic to the Steinberg group. And the isomorphism is by taking apartments. Cool, right? So this is a different way of thinking about Steinberg modules. They're groups of polytopes up to subdivision. All right.
Ronnie and Bob tell us what the two syzygies are. Do you know what the two syzygies are from this perspective?
I'm not sure at this moment. So I'm just going to focus on the generators and relations and pretend that syzygies don't exist. All right, cool. So I confessed to using this as a black box when I got into scissors congruence and starting to prove theorems, but at some point I became curious about how it was proven. And it turns out that when you prove it, there's a lot of kind of cool tricks you can use. And those cool tricks lead to generalizations of theorems that I was interested in before that have cool consequences. So I wanted to take a little bit of time and actually go into some details of how you actually, not the full proof, but like what are kind of the interesting parts of the proof of this. Okay, so the first interesting part is, why is this map well defined? In other words, how do you actually prove that the sum of the apartment classes for all these pieces agrees with the apartment class for P? Yep.
Sorry, still a follow-up for the. So is, maybe also a stupid question, is T of En actually a building in the sense of?
Is it actually what?
It's not. It is not actually. Is T of En an actual building in the sense of what a building? I mean, in the sense of a Tits building.
No.
Okay. If it's not, then maybe also what? Then maybe this is also not a. Okay, then spherical is also not the Solomon-Tits theorem or something, but it is a known thing that this is a spherical complex.
Yes. Yeah.
But it's not by Solomon-Tits, right? So it was known before your work that this was a spherical thing?
It's a classical one.
Huh?
The spherical one is the classical one that Solomon is present in.
Yeah, this is the classical one.
No, the first row of
But I'm bad on the history. I know that this is true, but I'm bad on the history of it.
Okay, but this is not something you proved, somehow this is a thing that also, okay.
Yeah. I mean, the tricks that I'll show you are, essentially the tricks that you need to check directly if this is true. Or at least one way of doing it. The kind of more geometric or polytopy way of doing it. Okay, so why is this well defined, right? So you have kind of a challenge here, because you think about subdividing all these pieces. The subdivisions don't match up exactly with the subdivision of the boundary of P. So there's kind of this trickiness involved in like getting things to line up. And it seems kind of difficult and complicated. It turns out, though, that there's a slick trick here that makes this really easy to check. Okay, so what's the trick? So first of all, let me redefine apartments a little bit. So I'm going to suspend the apartment map. And now this is going to be a map from P modulo its boundary. So I'm going to take the boundary of my polytope and quotient it to a point. It's a topological quotient, not a fraction. There have been so many different kinds of math in this conference, I guess it's important to say that. And now it's going to go to the cone on the Tits complex, modulo the Tits complex. And so now what is this in terms of posets? So this is realizing I'm now allowing my subset to be all of Euclidean geometry, and then I mod out by the subspace where it's not allowed to be Euclidean geometry. So I've added this extra cone point, this terminal object to the poset, and then I mod it out by the original poset. Okay, and you can kind of imagine how you do this, right? I drew this apartment map over here. And so I, say subdivided the whole boundary of the polytope. Well, to extend it to the middle, I just add another point in the middle. Right, now I've subdivided the whole polytope, and that extra point in the middle should just go to En, right? It should go to the whole space. Okay, so you can do that. But there's a little bit of a better way of doing it. So instead, we're going to say a map from P to this complex is apartment-like, or a quasi-apartment, if for all faces F and P, so let's call the map A of F is contained in the subcomplex of spaces that are properly contained in the span of F, or sorry, not properly contained, that are contained in the span of F and may also be equal to the span of F. Okay, so I'm basically naming a contractible subcomplex inside and saying F is only allowed to go there. Okay, so this is my polytope P, and P has to go somewhere in this contractible space. My condition is telling me, purple needs some love. My condition is telling me that for any face F, there's some kind of designated playground for F. There's some designated playground, and F is only allowed to go somewhere there. It can go wherever it wants, but it has to stay in that subcomplex. And now you do this for every single face of the polytope. So you do it for the vertices, the edges, the two-dimensional faces. You do it for P itself. Okay, so a couple of observations. The standard apartment is apartment-like. It satisfies this condition. And also, the space of apartment-like maps is weakly contractible. The zero homotopy groups. This is not too hard to prove. It's weakly contractible. So what does that mean? So, right, sort of think like a homotopy theorist. Having a contractible space of choices is just as good as having one choice. Right? It's like in Oscar's E infinity structures, having this contractible space of commutative multiplications. Well, actually, in that case, it's better. But in this case, it's equivalent. In particular, this means that any two of them are homotopic. And so if I give you any apartment-like map, it is homotopic to the standard apartment. So now that you have this principle, and now that you're thinking a bit like a homotopy theorist, this now becomes easy to check. Right? I now take my polytope that's subdivided. I'll just go back up here for a second. I choose apartment-like maps on all the pieces in a way that agrees along the boundary. And then when I do that, the result is an apartment-like map on all of P. So there's no combinatorics. There's no taking subdivisions, like moving things around, comparing the. You just say, well, they must be homotopic because they both live in the same contractible space. And so now, so I should put this up here.
So the standard apartment map is actually a cone point in this space, right?
Yeah, the space is weakly contractible, so you could, let's just say it's contractible. So yeah, you could deform everything to the standard apartment.
I'm saying it actually has a cone point, this space, which is the standard apartment, because you can like make all the things that you map to just be F.
That's morally true.
Okay.
It's actually, if you map any complex into the space, then you can deform that complex to constant map that all goes to the standard apartment, which is good enough.
Yes.
Yeah, okay, so now you just choose all these apartments, and so now, when I map from P mod dP to Cohen on Tits mod Tits, I can now take the apartment map here, and the apartment maps on each of these pieces, and I get a diagram that strictly commutes, where the map from here to here is just a collapse map. So I take all the edges that are in the middle of P, and I just crunch those down to the base point as well. That ends up in the wedge of these smaller polytopes modulo their boundaries. So yeah, so you kind of think a little bit homotopy theoretically, and instead of doing hard combinatorics, you just do some easy homotopy theory. Right? You just deform this map to the sum of these, and therefore this class and homology is the same as the sum of these classes. That's how you show it's well defined. All right. That's fun. Okay, so now let's prove the rest of it, right? Like now let's prove it's an isomorphism. So now to do this, I'm going to do the standard trick of stating a harder theorem and then proving that instead. Okay. Because it turns out that actually, so when I talked about taking, all the way over here, affine subspaces of Rn, I didn't actually have to take all of them. I could take any collection of hyperplanes and their intersections, and the theorem would still be true for that. Okay, so let H be a collection of, any collection of hyperplanes. Yeah, I guess I should disambiguate here, because H has meant other things this week. So H is not a Hopf algebra that may or may not exist. H, in this talk, H is a set of hyperplanes. And it definitely exists. Okay, very good. And then let's let L be the set of intersections of these hyperplanes. Okay, so for instance, I could take all hyperplanes, or I could take just these ones. And this, again, could mean all possible horizontal and all possible vertical lines, or maybe it could just mean the ones with integer coordinates, or the ones with rational coordinates. You could even do something fun like this. Nice fence pattern. And again, you could take just those, or you could keep scaling the picture down and down infinitely far. Or you could even just, I don't know, like take those, and then those, and then we're done. All right, so take any collection of hyperplanes. Okay, then I can adapt the two definitions that we've already seen. So I can let T L of En be the realization of same poset as before, so subspaces of En, but the subspace has to be in L. And so I'm restricting my Tits complex, and I'm only considering the subspaces that show up here. And then I can let the polytope group, the L polytope group, be same group as before, but I'm only going to use polytopes P such that for every face F, the span of F is one of these subspaces in L. So in other words, I'm only going to take polytopes that lie along my given subspaces. So, right, so for instance, I could, in this example, take this trapezoid. That's fine. Or in this example, I could take this rectangle. Here, there aren't that many possibilities, right? This is like a puzzle that you get on the side of your cereal box. How many polytopes are there here? I think there's only 3. Okay, so the polytope group for this one is very small, right? There's this triangle, this trapezoid, and the big one, but the big one decomposes into the small ones. So in this case, the polytope group is just 2 copies of Z. Okay. How you doing so far, little guy? There you go.
So H could be infinite when you said that.
H could be infinite. Yep, it doesn't have to be. Okay. So now the theorem, and this is joint with Cooper's, Leman, myself, Miller, and Sroka. I guess 3 of them are here. Is that if L contains a 0-dimensional subspace, so if we put this mild condition on L, certainly true if I take L to be, all subspaces, then this L Tits complex is again a wedge of n-1 spheres, and the map from the L polytope group, given by apartments, to the n-1st homology of this L Tits complex is an isomorphism. So that's all you need. It's actually really minimal. You don't need to take all subspaces. It doesn't need to be everything with coefficients in a certain field. Just name whatever hyperplanes you want, and the theorem works.
What if you drop the assumption on subspaces?
So exercise. You get a conclusion from this theorem even if this assumption doesn't hold. So if this assumption doesn't hold, think about what happens, and think about how you can still deduce what this homotopy type is and a presentation of it from this theorem. So this does actually cover all possible collections of hyperplanes. Yeah. All right. So for the proof, I've already told you the first part. This works just as well if you restrict your polytopes to things lying along L. So let me just tell you about the rest of it. The proof is, and this is actually going to kind of harken back to something in Danilo's talk, it's by induction on the dimension and induction on the number of hyperplanes. All right, so the advantage of stating the theorem this way is that it permits this kind of argument. Right? You can do an argument where you just add one hyperplane at a time and check that it's true. Okay, so now I'm waiting for someone to object. Me saying do induction, right? Because I never said finitely many hyperplanes, right? Of course, yeah, transfinite induction is a thing that we can do. We are lovers of the axiom of choice here. So by transfinite induction. Okay, so how does this go? So assume we've proven it in all 4 dimensions. Then the base case of the induction is I assumed that there was a 0-dimensional intersection. So I can just assume that I have some coordinate hyperplanes. I have to affine change of coordinates, this is true, intersecting at this point. And then I say, okay, polytope group here is 0. A polytope has to be bounded, right? So I only have unbounded regions cut out by these hyperplanes. And similarly, the Steinberg group is 0, because if you think of the poset of these intersections, their inclusions, that point is an initial object. Okay, great. So now let's do the inductive step. So there's some hyperplanes, and now let's draw one more. Okay, so I'm going to add this new hyperplane U. Okay, so how does everything change when I add U? It's kind of a fun thing to think about. Just draw this picture. Well, a couple of things change, right? So one is that new polytopes are created. I now have this one that I didn't have before. Let's do them in orange. And I have that one. And I actually have a choice of which of these two to do. Right, so some new polytopes are created. And also, the Tits complex is also changing. Right? I'm adding in these subspaces, and then I'm adding in U. So if you think about it, when you add in these subspaces, so these are the things that are in U intersected with L, that actually doesn't change the homotopy type of the Tits complex. The new one deformation retracts onto the old one. When you add this very last one, now you add one new vertex, and the homotopy type changes. But that's fine, because it's just one more vertex, so we can look at its link, and we can figure out how did the homotopy type change. So it turns out what happens in this case is that PT and ST both increase, so you can show that they get bigger. And what do they increase by? Well, PT increases by the polytopes that are in U that were cut out by L. So PT increases by the polytope group, but inside this hyperplane U of things cut out by L. On the other hand, ST increases by the Steinberg module in U of things cut out by L intersect U. So they increase by the same thing. And now there's a little bit more work to do. You have to make a comparison map of short exact sequences and use the 5 lemma. But by induction on dimension, you've already shown that the map between these is an isomorphism. And so now you get to conclude that the map, after adding the hyperplane, is still an isomorphism. This is also a place, by the way, where thinking in terms of apartment-like maps is really helpful, because each of these new polytopes your apartment-like map is a map from Q, comma, boundary of Q into some complex. And then you have a connecting homomorphism. You end up taking the boundary and then taking the piece along U, and then you get this face of Q modulo its boundary. And that's exactly the apartment map for this face. That's how you prove it.
In the case where you have finitely many hyperplanes, is this like a lift of Zaslavsky's theorem on the number of bounded regions?
Oh, Zaslavsky is at Binghamton, so I should know this. I'm gonna have to think about that. Yeah, of course, when there's infinitely many as well, then you have to think a little bit more carefully about, why are the new polytopes exactly the ones cut out by the old ones? So you have to crack open your copy of Ziegler, Lectures on Convex Polytopes, and do a bit of geometry. That's a good question, thank you. Okay, awesome. So yeah, Tits complexes are generated by polytopes, in addition to, I guess, polylogarithms and Charbleys and, I don't know, probably turtles. There's probably a million ways to present these things. All right, so why was I interested in this? Scissors congruence. I love scissors congruence. And this turns out to be a really useful fact to know if you're trying to do scissors congruence. All right, I should put this board up. Okay, so what's the connection to scissors congruence? Well, I mean, you can kind of already see it here, right? This is a presentation. It's saying that the Steinberg module really is some kind of group of polytopes up to scissors congruence. The only thing is I'm not moving them. I'm cutting it into pieces, and then all the pieces are staying fixed. So more generally, there's this group K0 of ENG. So this is the group of polytopes up to G scissors congruence. So G is some subgroup of the isometry group, or a subgroup of the group of affine transformations. And this has a formula. It's the polytope group. There's a strange sign factor, and that's G co-invariance. So you basically just take this group and you take G co-invariance, and yeah, right? Then you get a group where you can cut things into pieces, and then you can move individual pieces around by different elements of G. And so by this isomorphism, that's the same thing as the affine Steinberg module, tensored with a sign representation, and then you take G co-invariance. Okay, what's the reason for the sign? Well, it's because if I have an orientation reversing isometry and it sends a polytope back to itself, in the Steinberg module, that apartment class is going to get negated. But in scissors congruence, it shouldn't be. It should be the same polytope, even if I reflected it. So the sign factor shows up in order to correct for that. It just kind of undoes the flip that's happening algebraically in ST. Okay, so it turns out, I'm really not going to do this justice. There's this thing called higher scissors congruence, which is, among other things, gives you a sequence of groups generalizing this group. Higher scissors congruence. So it produces a spectrum called K of ENG. You can think of this as some group-completed space of polytopes up to G scissors congruence. In particular, it has K groups. These are, by more work with Coopers, Leman, Miller, and Soroka, three of whom are here. This object has K groups, and these K groups are indecomposables of the homology of some group of scissors automorphisms. So basically the same story with GLN happens here, except instead of matrices, the group that you're studying is this group of all ways of cutting up your polytope into pieces and then rearranging the pieces in some crazy way in order to make the same polytope again. So it's some very big, complicated group. But the homology of the group is, or at least its indecomposables are expressed in terms of this rationally.
Yes, okay.
Yeah. Sander's happy.
Is there not an issue of like K0, and also maybe you should say that you can pick any polytope, but it needs to be non-empty?
Yeah. Sure. P is non-empty. Good. Okay, so this is kind of the flavor of what this thing is and its significance. But it turns out there's a formula for this thing. So this can be expressed as, instead of taking the Steinberg module, I actually take this complex, the suspension of this Tits building, Tits complex. And then in place of the sign representation, it turns out there's a way of desuspending this by the tangent bundle of the geometry. So you can form a Thom spectrum, like formally desuspend it, and then you take the homotopy orbits along G. So we get a formula for this higher scissors congruence that parallels this very concrete formula in terms of the Steinberg module. This is a combination of some of my own work and work by Bowman, Gerhardt, me, Merling, and Zakharevich, aka Big Mamas. All right. Right, so we got this nice formula. Yeah. Oh, right, and these are cool mamas. All right. So we got this formula for K-theory, for scissors congruence K-theory. And from this formula, at least for one-dimensional geometry, you can now write out what these groups are. So let me just do the line. I'll take the full isometry group of the line, so all translations and reflections. So K0 is R. That corresponds to the elementary facts that if you take line segments up to cut and paste, the only invariant is their length. We added negatives because it's K-theory. K1 of E1 is 0. This was a result of Zakharevich from before this formula. And then K2 turns out to be the third exterior power over the rationals of R. K3.
K2,
it's not a typo, it's a thinko. No, it's a typo. Yeah, E1. Sorry, this is all for the line. We don't know what it is for E2. K3 is 0. K4 is lambda 5. And the pattern continues. So we can actually, at least in dimension 1, we can use this formula to compute what these K groups are, and therefore get indecomposables of what are essentially interval exchange transformations, except you're also allowing flipping. Rad. Okay, so this is really fun, but as soon as you go above dimension 1, it gets super hard. Right, so there's this problem. If this gets really, really hard above one-dimensional geometry. I don't know if you guys know this, but like computing homology of a group is really hard. Okay, so what's the solution to this? Well, the solution is to cut out kind of easier, smaller, simpler versions of this that we can understand. And then from those simpler versions, we can build our way back up. And so that's exactly what this version of the theorem allows us to do. So this version, the Solomon-Tits theorem, turns out to be the key ingredient in proving this formula. So once we have this theorem, we can prove this formula now. So now this is going to be, this is bad board work. So now I'm just going to say L polytopes, and I'm going to take the L Tits complex. And now that formula is still true.
L has to be G invariant or something?
Yes, yeah. G has to preserve L, otherwise this won't even make sense. But once it makes sense, it's true. Yeah. Okay, so now you can study variants of this where you've severely restricted what your hyperplanes are, or you've severely restricted what your group of transformations is. I guess you could have done that before. And you get into some pretty tractable cases. So for instance, I mean, in the one-dimensional case, this allows you to look at things like Thompson's group V. You can study that through this cut and paste framework. You can get a new proof of Zhimik and Wall's result that V is acyclic. That's fun. You can also go up to dimension 2, which we don't know how to compute, and you can look at polytopes that have rational vertices. And so then, using this, you can then get a computation of that case. So this is going to be, I'll just show you because just for fun. So this is an exterior power of a direct sum over all primes congruent to 1 mod 4 copies of the rationals when m is even and 0 when m is odd. And so although for scissors congruence of the plane, well, Lydia Hawley is doing her thesis right now and is proving some great stuff about that, but it's kind of unreasonable to expect we're going to be able to really completely understand a presentation of those groups. If you're strict to rational vertices, then you can.
P equals 1 is included in this as well, right? Because
The relationship
this is
SU mod S.
This is supposed to be Gaussian primes that are not real.
Oh, I don't know.
So I think P is 1 is not included.
Well, these are prime numbers.
Oh yeah, those are primes congruent to 1 mod 4.
I see.
Yeah. This has to do with Pythagorean triples and imaginary Gaussian primes.
Usually
Yeah. This has to do with all the ways that you can rotate with rational coefficients. Right. The point is, it's a thing that you can actually do because the group is small enough and tractable enough.
What's the group in this case?
SO2Q, so rotations with rational coefficients. SO2Q, this really beautiful theorem that this is isomorphic to a cyclic group of order 4 plus a sum over these same primes P of Z's. Yeah. And the proof of that is beautiful too. All right. This also, how much time do I have left?
about 2 minutes.
About 2 minutes. Okay.
How many minutes you go over?
All right. Well, I'm going to say this, and then I guess I'll draw some cubes. So this also allows us to connect. Let's say it this way. Right. So this also allows us to give a geometric interpretation to the homology of SLNZ with coefficients in Steinberg of Qn. Right? Because we can now restrict our polytopes and we can restrict our group. And so we can, scissors congruence is originally this thing where you're approaching something very geometric and you're thinking in terms of the real numbers. But if you make the framework flexible enough, you can use that geometric intuition to say that, well, to interpret this. And so this is also a direction that I'm pretty excited about. And hopefully you are intrigued by as well, given the content of this conference. Right, so the Church-Farr-Putnam conjecture and the vanishing of these groups in a certain range has a geometric interpretation using this technology. Roughly, a statement about spherical polytopes up to SLNZ action and scissors congruence classes and the indecomposables of scissors automorphisms vanishing in a certain range. Okay, so I don't have a lot of time left to talk about the last thing, so let me just say the last cool thing that I was going to talk about is that when you have these apartment classes, let's go back to the linear Tits building, n-1, yeah. Hopefully I'm getting the grading right. Maybe Peter can correct me if it's wrong. When you have these apartments in the linear Tits building, you can suspend them. So this is now delta n-1 mod its boundary, going to the suspended Tits building. It turns out when you suspend these apartments twice, So now I've taken this simplex and I've coned it off. But I really should say I subdivided it. Take the subdivided simplex and cone it off. It turns out something really cool happens. This, as a simplicial complex, is the standard simplicial complex for the n cube. So in other words, when you suspend departments twice, they become cubes. And it turns out that thinking of apartments in this way is really useful for thinking about products and coproducts on these spaces. They get a cubical interpretation. So in the Hopf algebra structure that we've seen in a couple of these talks, when you take the product essentially becomes taking a product of two cubes, and that gives you a cube in the product space. And when you take the coproduct, this is even cooler. When you take the coproduct in one of these cubes, the interpretation is that the cube gets cut up into 2 to the n subcubes by cutting along all the hyperplanes where each coordinate is equal to a half. And then each of these smaller cubes, so when you write out the coproduct for this, each of these smaller cubes ends up getting identified with one of these cubical apartments in the parabolic product of these two Steinberg modules. So you get this really cool, really nice looking geometric interpretation. And you can use that to take this Hopf algebra structure that we were discussing before and write down its coproduct in a topological way. In fact, you get an E1 coalgebra structure, where specifically you actually get a coaction by the little intervals operad. So this co-multiplication turns out to be the one that you get from taking the interval and cutting it exactly in half. Like that. So you can start to imagine, well, what if I just have 2 little intervals inside? What happens? And well, you take those 2 little intervals and you draw them in each coordinate direction, and then you take all their products, and you get these 2 to the n cubes sitting inside with some interstitial space in between. And the map then becomes the map that collapses all that interstitial space down to the base point. And then you still get a wedge of cubes modulo their boundaries, and then those go to the appropriate classes on the right-hand side. All right, that's all I got. Thanks for listening.
Questions? So in the coproduct, in some sense, when you have something, this is something 3-dimensional, you split it into something 2-dimensional, something 1-dimensional, right? Where the 2-dimensional thing is a sub and the 1-dimensional thing is a quotient again, right?
Yeah.
Is that correctly?
So go to a wedge over U and V, double suspension of STU, smash sigma ST of V mod U.
Yeah.
Right, so here you have some cube which is n-dimensional, the dimension of V. And here you go to a wedge of cubes. So you take, some basis. Your apartment's given by some set of vectors V1 through Vn. And for every subset of that, you get a cube of dimension the size of S. Let's just call this n. Like that. And so you define this map sort of directly topologically. You actually get a whole family of maps because you have a lot of ways of putting 2 little intervals into an interval. But for each of those maps, this cubical apartment here just goes directly to this wedge of products of cubical apartments over here. So it's kind of like, it works out topologically way better than we expected, basically.
Any other questions?
Yep.
Maybe stupid, but does it make sense to ask for the same thing with hyperbolic geometry instead of Euclidean or like?
Oh, yes. We also prove a version of this for hyperbolic geometry. I didn't state it in the talk. And also a version for spherical geometry. But for spherical geometry, it turns out it takes longer to state the different forms of it and how they're related. And that's because the sphere isn't contractible. It turns out there's actually 2 forms. One which has to do with unreduced spherical scissors congruence, and the other has to do with reduced spherical scissors congruence. But yeah, absolutely.
Well, we'll have lunch, and that's the last meal we have together here as from the conference. Thank you all for coming. Let's thank Carrie one more time.